This video will go over the answers to the pre-test of the Year 12 review, which is our starting point for our Level 3 study of circular motion. So, firstly, we're asked to state the direction of the acceleration of Alex on a merry-go-round at constant speed. So the direction of the acceleration is always towards the center. Whoops. Let me just fix this. Towards the center. And we call that type of acceleration centripetal, which is a word that means towards the center. The second question is, how can something moving at constant speed be accelerating? We can say the velocity is changing because the direction of the velocity is always changing, or because the direction of motion is always changing. And if the velocity is changing, then the object is accelerating. So the object is accelerating. Oops. Name the force acting on Alex. Well, we call it the centripetal force. We should note that the centripetal force always needs to be provided by something acting on the object. So in the case of a person standing on a merry-go-round, it might be the friction of the floor of the merry-go-round acting on the person's feet. Okay, question 4 says, what happens to the force on Alex if the merry-go-round speeds up? Well, Fc is equal to mv squared over r. So if v increases, Fc will increase. I'll write the equation for centripetal force. Well, we've already done that up above, but we can write it again. Fc is equal to mv squared over r. The equation for centripetal acceleration, AC is equal to v squared over r. We need to recognize these. We are given them on our formula sheet, but we do need to recognize that that's what those are for. The units for centripetal force will be newtons, as for any force. And then we're asked to give 3 different examples of circular motion and say what provides the centripetal force. So we can talk about, for example, the orbit. The orbit of the moon about Earth. And what provides the force there is the gravitational attraction of Earth on the moon. So force of gravity on the moon due to Earth. A second example might be, for example, a ball twirled on a string. And the force here will be the tension force of the string on the ball. And a third example might be, for example, a car on a roundabout. And in this case, the force acting on the car is the friction force of the road on the car. So in some way the outside world needs to provide a force on the object, pushing it towards the center. And whatever force that is, that's going to be what provides the centripetal force. Okay. So the next question says, we have a 0.5 gram ant clinging precariously to a spinning turntable. The radius is 20 centimeters and it's spinning at 40 revolutions per minute. So we should note here that that's grams and that this is centimeters. So the radius here is actually 0.200 meters. and the mass here, m, is equal to 1 gram is 10 to the minus 3, so 0.5 grams is going to be 5.0 times 10 to the minus 4 kilograms. Calculate the period of the turntable. The period is going to have something to do with this number here, 40 revolutions per minute. So in 1 minute, we have 40 revolutions. So in 60 seconds, we have 40 revolutions. And we want to know how long it takes to do 1 revolution. So t is going to be equal to 60 seconds divided by 40, because we have 40 revolutions in 60 seconds. So that is 1.5 seconds. Calculate the ant's velocity. Well, v of something moving in a circle, in 1 period, it will move 2 pi r meters. So we can write that v is equal to distance over time. And the distance it covers is 2 times pi times r. And the time that it takes to cover a full circle is 1 time period. So in this case we have 2 pi times 0.2 divided by 1.5. So let's figure out what that is. 2 times pi times 0.2, and we divide that by 1.5. So 0.62. Hold on, that's not right. Let's try that again. 2 times pi times 0.2 divided by 1.5. It's 0.8377. So 0.84 meters per second. This equation here is a good one to know. We can easily work out the speed of an object if we just know the radius and the period. Calculate the centripetal force on the ant. Well, we know that centripetal force is mv squared over r. And we worked out before that the mass is actually very small, it's only half a gram. So it's going to be equal to 5.0 times 10 to the minus 4 times v squared, that's 0.84 squared, over 0.2, which gives us, so we have that v here, so we can go 5 times 10 to the negative 4 is the mass, times the speed, which we had, which is 0.837758, squared, and we divide that by the radius, which was 0.2 meters, which is 0.00175, or 0.0018 newtons. Okay, so note that in my calculation here I used an unrounded or a less rounded number just to make sure that my two significant figures here would turn out to be right. What is it that provides this force? Well, it's the force due to friction. So it's friction of the ground on the ant. Explain why this force does no work. Okay, so work is done. So work is force times distance, but we only take the component of the force that's acting in the direction of motion. So we can say work is equal to force times distance times the cosine of theta, where theta is the angle between the force applied and the distance moved and the direction moved. for circular motion, it's always moving tangentially to the circle, and the force is always acting towards the center. So those two are always at right angles to one another. So if you have an object moving in a circle like this, then the direction of motion is this, and the direction of force is this. So for circular motion, theta is 90 degrees as F and V are perpendicular. And cosine of 90 is equal to 0, so no work is done. Okay, basically if the force has no component in the direction of motion, then that force will not do any work. So if the force and the velocity are at right angles, then the force will not be doing any work. Alright, F. The maximum friction force between the ant and the turntable is exactly double this. How fast could the turntable spin before the hapless insect falls off? So basically here what we need to do is use the equation F is equal to mv squared over r, and we know what the force is. It must be double the one that we had up here, which was 0.0018, and we know the mass and we know the radius, and we can then find the speed at which that force is reached, at which the centripetal force is equal to the maximum friction that the turntable can provide. So if we rearrange this for V, we get V is equal to F times R divided by M all square root. So we want double that force of 0.84. So we are going to have the square root of 2 times 0.84 times the radius, which was 0.84, is 0.0084, times the radius, which was 0.2, and we divide that by the mass, which was 5.0 times 10 to the minus 4. And that gives us hold on, have I got the right values there? Let's just check. What was the centripetal force? It was 0.0018, sorry. That's the centripetal force. Okay, so let's do that. So 2 times 0.0018 times the radius, which was 0.2, and we divide that by the mass, which was 5 times 10 to the negative 4. And we get this, and we need to square root that, which is 1.2. Oops, equals 1.2 meters per second. So if it spins faster than 1.2 meters per second, then the centripetal force required is more than the maximum friction that the ground can provide on the ant, which means that the ant will start to slip off. And the direction that she will slide, if we assume that friction just suddenly drops away, is going to be tangential to the circle. That's if the friction suddenly drops to 0, which it won't quite. But basically what we're getting at in G here is that if we remove the centripetal force, then the object will continue with the speed that it had in a straight line. Okay, so I recommend that if any of these ideas feel rusty, then you should go over the assignment from last year. There's a link to that in the work document. Okay, so if all these ideas feel pretty comfortable, then you should be set to get started on the new level 3 circular motion content.